Okay, so we have looked at two representations of multilinear polynomials now, right? We looked at dense and we looked at sparse. There's another way. I'm sure there might be more ways, but there's another way. Can anyone think of what that other way might be? So let's think. What way can that be? Like that is different from what we have done so far.
It's not dense.
It's not dense. It's not sparse. It's not dense sparse. It's not FFT. It's not sparse dense.
It was.
What HT? HT? Oh, HC. Yes. The evaluation what? What's the evaluation method? So explain it. Explain it. What do you think that might look like? So she has given a clue. So just think a bit about what that might look like. Is there evaluation something? It doesn't matter now. Okay. Well, you guys should listen now.
Listen.
She said evaluation representation of the polynomial. I mentioned what yesterday? So what would that look like? What So you evaluate it. Okay. Yeah. So there's coefficient form representation, and then there's evaluation form representation. So what we have been looking at so far has been coefficient form rep. And we looked at two ways to represent the coefficients, right? We looked at the dense and we looked at the sparse. By the end of the day, they were all dealing with coefficients, right? So like in dense now we had like A, B, C. So what we just put in the array is the coefficient of A, B, C, right? So I've always been dealing with coefficients. Then sparse is just like dense but without the extra stuff. But now, remember that we said that let's say a two-variable polynomial, you can write it a different way, right? You can write it 0, 0, 0, 1, 1, 0, 1, 1, right? And then evaluate it. So those evaluations is another way to write that same polynomial. Do you get? So, yes, I'm going to down. Let me show my screen. Okay. So now, let's say we had a two-variable polynomial, f of a comma b, which is equal to 2a plus 3b, right? So this is our polynomial. This is coefficient form representation of this polynomial. But then, we can encode exactly the same information in the evaluation form, right? And we use Lagrange to go backwards, and we use evaluation to go forwards. Okay, so this is the same thing as having 0, 0, 0, 1, 1, 0, 1, 1. So we just evaluate over the Boolean hypercube, right? And then what would this be? This would be 0, right? What's this? What's this? What's this? So what we're now saying is that you could represent this polynomial as yes, you can represent the same polynomial, you can represent as this. So now let's say we wanted to, there's a naive way to do everything that we want to do, right? What we could do is let's say you wanted to evaluate at a something, a comma b, right? You could use your multilinear Lagrange interpolation, right? To interpolate first, so you get this one back, and then you now evaluate at whatever a, b is, and then you get your answer. But that's dumb, right? So like, why did we now go this way? So the question now is like, can you evaluate this or partially evaluate this without interpolating?
Yes.
You say yes. You know how to do it.
Use the powers of use the power.
Okay, wait. Yes. So, no, normally when you have the polynomial, this is this, right? F of a comma b is equal to 2a plus 3b. So let's say I wanted to evaluate it at a equals 1, right? So that's f of 1 comma b, right? So that's what? 2 times 1 plus 3b, right? Which is equal to 2 plus 3b. So this is the result of partially evaluating that at a equals 1. What's the evaluation form of this? So now it's one variable, right? It's just b. So it's just 0. So that'll be what? So my question is, can you go from that to this?
Sorry.
So we need to make sure you are seeing ideas, right? So we'll get back. But we need to make sure that everybody understands the problem statement or the environment that we are dealing in now. Was that what we did yesterday? So you know how to do it?
No, but like this, that one that you said, check zero and check one.
So that check zero and check one is multilinear Lagrange interpolation, right? So it can take you from this back to this. Or it can take you from this one back to this one. But what I want to do is I want to partially evaluate that at a equals 1. I want the results to be without going through. So there's one way to do it, right? We could do this, we could interpolate it, right? So we could do like this 0, 3, 2, 5, right? Then we do interpolation, right? Then we're going to get what? 2a plus 3b, right? Then we partially evaluate at a equals 1. So we're going to get 2 plus 3b. Then we now do the what? Evaluations. So we'll now get what? 2 and 5. Right? This is how we could have done it. This is the naive way of doing it, right? The question now is there a way to just go from with what?
You find all the cases that A and 1 are going to.
Uh-huh.
You know that A is always 1 and 2 guys. Like 1, 1, 0 and 1, 1. A is always 1. So the last two A is always 1. So we can evaluate 2, 5 is equal.
Yeah, exactly. So that's 0, 0, 1, 0, 0. The same way you are like, for that, for the representation you use,
Let's pull up the
based on the representation you use,
Yeah.
you're subtracting 1 from every.
I talking about the dense?
Yeah, from that, like.
The dense coefficient form.
Yes.
Okay.
You're subtracting 1 from every index where,
Uh-huh.
like, A is present.
Yes.
So if you like look at this same evaluation,
Yeah.
you have 0, 0, 0, 1, 1, 0, 1, 1.
Yeah.
So pick the indexes where you know we say A is.
Want to evaluate a at 1, okay?
Yes. So
Uh-huh.
if you want to evaluate A at 1, but the 2 is a 2-digit bit.
Yes.
So that means A is the first digit, while
Yes.
B is the second.
Uh-huh.
Now look at through the array
Boolean
and
hyper.
find the ones where A is 1.
Uh-huh.
And then that should represent like, I don't know, I'm close, but
You are close and you are far.
It's already in the evaluation form.
It's already a relation form, yes.
So it means that, like, basically, if you're evaluating at A equals to 1,
Yes.
you're basically just going to check all the cases where
A is equal to 1. Okay, so now let me ask this question. If I want to evaluate this at 1, 0, what will be the answer? 2. It's obvious, right? Because this is already the evaluations over the Boolean hypercube. So it's already stored there. So we don't need to do like 1, 1 here, then 2 times 1, and 1, 0 here, sorry. Then 2 times 1 plus 3 times 0, which is 2. Right? We don't need to do that. It's easy. It's straightforward. So if I want to evaluate at 0, 0, what would it be?
0.
Cool. Now, if I want to evaluate this at 2, 3, for example, let's say A is 2 and B is 3. Now it's no longer here, right? So how will you do it? This is the one we're not talking about. Like you want to be able to evaluate it anywhere. Or partially evaluate at A equals 3, or A equals 18, or A equals 9. How do we do that?
Maybe you can, when you zero index for that.
Uh-huh.
Then B, what there's one index. I don't know. Okay, that's two. I don't know. According to the index.
Oh, according to the dense. Okay.
According to them, says then C is 4. You
Mm-hmm.
can pass it since you already know what you're doing, right? And pass it the position of the.
Oh yeah.
Or maybe
Yeah, like let's
binary.
use the index. Since like this is 0, 1, 2, 3, right? Now the index of 2, let's say if you want to like evaluate the index of 2, right, is going to be 1.
Wait. Where's the index of?
The index of, okay, let's use the index of 5. The index of 5 is
Okay,
going to
okay.
be 3, right?
Yeah.
And now when you represent 3 in binary, it's going to be 1, 1. So
Uh-huh.
you say evaluate this polynomial as let's say x equals a equals to 3.
A equals 3. Partial divided by A equals 3. Uh-huh.
So you can now say, okay, since this guy at position 5, a is 1, 1, you can now say okay, 3 raised to power 1, right?
Uh-huh.
Plus
So you guys are close, but you guys are
Think
so
about something.
are far also.
So let's say you say evaluate at 9 and 10. I don't know if this is correct. So that 9, since this is 2 digits.
Yes.
If there's a way we can make 9 like in binary, so to be 4 digits, then we can split it into 2. So we can evaluate it 2, 2.
Okay.
When you evaluate 2, 2, we're going to get 1. We will not evaluate at those single ones. Like 9 is like, I don't know, 4
So
bits.
do you have an algorithm? Should we try something out?
Yes.
Yeah, let's do 2, 3. Let's do evaluate at 2, 3.
At 2, 3.
Yeah. Once evaluate this at A equals 1, sorry. Yeah. Or do you want full
Wait,
evaluation?
I thought you said we were doing something that was outside.
Sorry, A equals 2.
A equals 2.
Yes.
Okay, so 2 in binary
It's 1, 0.
is 1, 0.
Yeah.
That's like in 4 digits, that would be 0.
Why is it 4 digits? 1 for each. Is it because the length of the array is 4?
No, because we are dealing with 2 bits. And then something that is outside.
You're saying A is.
Something that is outside the Boolean hypercube has to be more than what it can hold. Like more than, I think the highest number there is 11. Like the binary is, yes, so it has
1,
to be
1.
more than 11. Yes, that's more than 1, 1.
Okay.
So if it's more than 1, 1, that means we like, let's say from 1, 0, 0.
Okay.
So if you have 1, 0, 0, we can do 0, 1, 0, 0 to make it 4 bits. Then we can split it into 2.
So let's just try it. No, I don't get it, but I'll get it as you tell me how to go about it. Or you don't know how to go about it.
That's just the idea.
You don't but I don't get the idea. But I know what the correct thing should be, and it still feels far.
what's it like there isn't that some check later?
No, we don't need some check yet. But let me hear. What do you mean?
I
Some check allows you to prove that the sum. So like 3 plus 2 is what? 5. 5 plus 5 is 10. Right? The sum over the Boolean hypercube is 10. So some check allows you to prove that the sum is 10 to somebody else without that person like adding up the numbers themselves. So how would I help you evaluate this at A equals 2?
So now you're dealing with A, right? You can now pick like the guys that are like where is 1, 2 and 5. Right? So like, right, maybe you write that out 1, 0, 1, 1, 2 and 5. Right? So you can now say how can you create any polynomial from this?
Uh-huh.
Right? So I want to like evaluate A is 2, right?
Mm-hmm.
Some check 10, 11. So we can just say still.
Okay. Let me give you guys one clue as to how the Boolean hypercube works. Okay? So this Boolean hypercube that we're looking at here is like level 1 understanding of the Boolean hypercube. There's a level 2 understanding, a more graphical understanding. Okay? So once I give you that will give some clues as to how one might do this. So the way we discovered all of this was we understood level 1, not for partial evaluation, just like Boolean hypercube is just all binary strings of a certain length. Right? But then like, why didn't I call it Boolean hypercube? Like, why is the cube there? What's all those for, right? So we now have to go and look at math itself, and then we saw the definition of Boolean hypercube. And in that definition, there's something very specific that I want to tell you guys now. Okay, so the polynomial hypercube, each this thing there represents a point, right, on a surface. Then there's a connection between these points, and you don't just connect one point with another point. There's a process that you have to follow before you can connect, or some condition must be met before you can connect it. Okay, so let's look at this 0, 0, 0, 1, 1, 0, 1, 1, right? 4 points. Okay, so the condition is that you can only connect 2 points if they are only different in 1 bit. So you can connect 0, 0 with 0, 1 because of, to make one the other one, you only need to change one thing, right? So you can change the last 0 to 1 and then it's exactly the same, or you can change the last 1 to 0 and they're exactly the same, only 1 bit difference. So what else? You can also connect to 1, 0, right? Okay, and then you can connect, so what can you connect 1, 1 to? 0, 1, 2, 1, 1, right? And 1, 0. So now you can see this square I was talking about for a 2 variable system. I think you can't see. No, you can just shift. No. You can't still do it. Maybe, I don't know. Does this make sense? The rule. Does the rule make sense? Are we getting it? No. Okay, so the rule is you connect. So when I say connect, I mean like you draw a straight line between the 2 points if they are labeled. So I'm calling the points labels like 0, 0, 0, 1, 1, 0, 1, 1. If their label is only different in one position, then you can draw a straight line between them. So like 0 and 1, this is the smallest one, right? It's only different in 1 bit. So hence we can draw this line. Make sense? But then 0, 0, 0, 1, 1, 0, 1, 1. We can't draw a line here. This line will be wrong. Right? Because of, let's say 1, 0 and 0, 1. How can we convert 1, 0 to 0, 1? We'll need to change the last bit to 1, right? And then we need to change the first bit to 0. That took 2 steps. Okay? Or you can just say that the first bit is different and the second bit is also different. You want that only one of the bits is different. So that's why this line is not possible. And likewise, but this one now, the first bit is different, but the second bit is the same. So it's only at one spot that there's a difference. Hence, you can draw a line. Does it make sense?
Yes.
Same with this, same with this, same with this. Cool?
Yeah.
So, given this graphical representation, let's now look at how the points are laid. So, 0, 0 is 0. 0, 1 is 3. 1, 0 is 2. 1, 1 is 5. There's a different way I used to explain it, but I don't know if I'll go that way. But let's see this. Let's see this. So the next place is 0, 0 normally. The next place is 0, 1, 1, 0, 1, 1, right? And then these guys are connected this way. So this means that this is 0. Like that's the evaluation, right? And then this place is 3. This place is 2. And this place is 5. So this is how this polynomial, not really how, but this one is supposed to be a 3D structure. I'm making it a 2D structure. Like it's flat. How it actually is that, I don't know if that's how it actually is. One will need to like verify with the graph and everything, but it's more like you have something like this. Right? So you have A here, and you have B here, right? So let's say this is 0, and let's say this is 1. Then it's also 0, and this is 1. So the way 2D structures work is that you use the A, B, you pick it on this flat surface. Then you project to the corresponding y value, right? So 0, 0 is right here, right? Because this place is 0 for both a and b, right? Then 0, 1 is here. If we assume that a comma b, right? So a is 0, then b will be 1. So this is 0, 1. You don't need to fully understand this part. I'm just trying to show. This is what we'll mostly be making use of, okay? I'm just trying to show what it looks like. Then 1, 0 is going to be here, right? Where a is 1 and b is 0. So this is 1, 0. And then 1, 1 is going to be somewhere here, right? 1, 1. So this is that square that I'm talking about, right? Like looking at it from the top. So now when you're choosing your values for 0, 0, 3, 2, and 5, that is 0 is 0. That means that the evaluations are going to be on this, let's say, z axis. Okay? So 0, 0 is 0. So that means that the evaluation will still be here, right? Then what? 0, 1 is what? 3. So 0, 1, which is this. Let's say this is 1, 2, 3, right? This is z, by the way. So that means that it will project it here, right? So 0, 1 on the flat surface, then you project it up to 3. Then 1, 0 is going to be 2. So this will project up to, I don't know if this is accurate, but I'll just say that this is 2 somewhere here, right? And then what? 1, 1 is what? 5. So that will be somewhere top. Let's say somewhere here. So then that will now mean that we'll have some structure that looks like, yeah, but on the space. So it's like the cube was flat, then the evaluations would it's like imagine like a flat surface here. Then when I put 0, 0 is this, it will either drag it up to a certain location. You get what I mean? So it just drags it up. So every different polynomial of two variables has a different shape when you drag, because we are going to drag it to different places. So 0, I don't know how to explain it. Well, like, let's say 0, 0 is here. Then this one will drag it up to 3. This one can't bend, but it's supposed to bend. And this one will drag it up to 5, so it's not going to be like this. And then this one will drag it up to something else. Do you get what I mean?
Like every polynomial represented as a shape or something.
Yes, something like that, exactly. In the space of its dimension. So like this one now is for 2 variable multilinear polynomials. But for 3 variables ones now you'll be using like so the base will now be like 3 points. Then the y is going to be 1 point. So you're going to be in 4D and like 5D and stuff like that. But does that make sense? This is just to understand what might be happening. But this is not necessary for what we're going to be using this other representation. Cool so far? Yeah. Okay. So now I've given you a clue. Do you have a question? Yeah. Okay. So is this polynomial here? That polynomial, this is the coefficient form representation of that polynomial. So what we're doing now is that we are trying to evaluate this polynomial over Boolean hypercube of length 2, because it's 2 variables. So we evaluate it as 0, 0. So a will be 0, b will be 0. That's 0. Then 0, 1. So then you can get it. So both of them are the same polynomial, just written in different ways. So what we're trying to do now is we're trying to figure out, can we still do things like partial evaluation and the likes on that directly without coming to this? Because that will be more efficient. We don't have to do like all those steps. Okay. Make sense? So let's continue. Now I give a clue. Does it help now? So this is 0, right? This is 3. I think this is 2 and this is 5, right? This is 0, 0, 0, 1, 1, 0, 1, 1. Don't mind my handwriting. It's fine. And then we're assuming that the labeling is like a comma b, which is what? 0, 0, 0, 1, 1, 0, 1, 1. So now if we wanted to evaluate this at a equals 2, and let's say b equals 3, how can we use this structure to perform that evaluation? Ahead. So she has said something now. She said the shape would change. Whenever so one variable is a line. Two variables is a square. Three variables is a cube. So let's say you started at a cube, that's three variables. And you evaluated at one variable. Your new structure will be what? A square. Right? You started at a cube, right? Which was three variables. When you evaluate at one variable, you are removing that variable technically. So it's now a two variable system. That two variable system is always representable as a square. Then if you evaluate again at just one variable, then you get a line. So partial evaluation is doing a reduction in dimension. Mm-hmm. Mm-hmm. Oh, we should do that. Okay. So she wants to see what it will look like when we partially evaluate A at certain values, right? So right now it is what? Right? That's what? 2A plus what? So let's partially evaluate A at 2, right? So f of 2 comma b. That's what? 4 plus 3b. What's the Boolean hypercubitization of this? Right? So what this means is that we have a straight line. I'm coming. Yeah, we have a straight line. Does it make sense? This is what it will look like. It does not make sense how we got that. But this is what does it make sense about it? So like a one variable system is a straight line. So 0, 1. But then you now put the values there on top of it. Does that make sense? So now let's say we evaluated B at 3. But we left A. So this is going to be what? 2A plus 3 times 3, right? 2A plus 9. So what will be the 0, 1? 9. And what will be the 1? 11. So this one now is a straight line, but it's a different kind of straight line. This is another clue. This is a clue. This is 9 and this is 11. This is a clue. It's a clue.
Why is one vertical, the other one is
That's the question. That's the clue. Every time you partially evaluate at one variable, there's a reduction in dimension. Right? So two variables had a square. Then one variable is going to have a line. Right? So because I only removed one. So now let's do partial evaluation at both A and B. Exactly. So we did at A and B. That's let's say 2, 3, right? That's 2 times what? 2 plus 3 times 3, right? Which is what? 13. So you just have that's because I've gotten rid of all the dimensions by partially evaluating the variables. Yes, this will be on the Y.
Isn't adding more value at different points?
What do you mean?
Like if we had 0, 3, 2, 5
Yeah.
for the evaluation,
Yeah.
like the initial system.
Yeah.
If we are evaluating say A at 2,
Yeah.
right, we get 4, 7 or thereabout. I don't know.
Yeah, 4, 7.
4, 7.
Yeah.
What I'm seeing
Yeah.
is that you're basically adding 2
2.
to the position of like
That's this one. right?
0, 3 to 5, right? You're basically adding 2 to, yes, that position at 5.
And 5.
Yeah.
Essentially. But I don't know if.
What? But it doesn't work for this now, right?
Yeah.
That's supposed to have given you
But that one
3,
doesn't
right?
have an
But
A.
that one does not have, like, it doesn't have a turn
It's a
up there.
constant.
If you get what I mean.
I get what you mean. So where will we get the 4?
That's where I.
That's it. Okay. So yeah. Okay. Any other ideas?
You have 9 and 11.
I'm left 13 also.
Yeah, we have 9 and 11, and we have 4 and 7, and we have 13. So what we're trying to do now is we're trying to understand the structure so well that we can make use of it to like do what we want to do, right? So once you understand the structure really well and you know what you're trying to accomplish, then you'll figure out ways to make it like bend to your will, kind of. So the more interesting thing now, what you should be trying to do is figuring out like how does this.
So when you evaluate,
That's not enough information. Overlapping. What? Yeah. What
when
is
you
it?
evaluate as A and
Yeah.
when is A for the 2 points where A is turned on,
Yeah.
if you multiply 2 times 3 is 6 and 2 times 5 is 10. 10 minus 6 is 4. Is that how
Wait,
it
2 times what? 2 times 5 is 10.
times 3 is
Or 2 times 3. You did diagonal multiplication.
No, I'm like multiplying the value of A at both points.
The value of A. Or where you're evaluating A, which is 2. As where? Where and where?
At 0, 1 and 1, 1.
0, 1, and 1, 1. Are you putting it at the back?
Just along the dimension.
This here.
Yeah.
Uh-huh.
That's 6 and 10.
Right.
And then when you minus that's how you get the 4. And it holds correct for when you do it on B. When you do it on B as well. But I don't know what that's supposed to be.
Wait. Come again.
If you, when you evaluate,
Yes.
so this 0, 1, 1, 1 line.
0, 1. So that's this one.
Yes, that's
Okay.
where A is turned on.
What do you mean? Why do you say that?
Okay, no, that's it's the other way.
So you guys need to somehow like forget about the dense and forget about the equation form and forget about the fact that not forget too much, bro. Have an open mind. You know what another clue? The other clue I'm going to give you is they are straight lines. That's the clue I'm going to give you.
Are you just like are you overlapping? Like
What do you mean overlapping?
like
Oh, you mean like it must have somehow compressed this and this, right, to
Yeah.
get this.
yes.
And the other one must have somehow compressed this and this to get this. Yes. I'll say yes. Let me just give you that clue. Yes.
But how?
But how does it compress it exactly? And why does it compress
It's
it?
like a ratio.
What do you mean?
Compression is because now this guy you're trying to look for A and A is the first guy. So if
Uh-huh.
A is the first guy, zeros and zero, like the first one
Please don't just
is
tell
zero
me.
is A. So you're looking for like the first one, like you're looking for A.
Uh-huh.
Right, so so you're going to like so you said
Is it someone is getting somewhere?
he said
And there has to
He said that it's a line.
the line
And a line has like a gradient and a constant.
Louder.
So if you want
No, the toast now.
It's not
Oh, yeah, you
So I
know.
understand what you're
You are not confident in yourself. Be confident.
Okay, I'm trying
Oh yeah, someone wants to try, yeah.
I'm trying to look at the first shape there.
The square.
Square. Then looking at this line, the 2 lines, the horizontal and the vertical.
Yes.
So since there is it's supposed to be 2 points, there's supposed to be I'm looking at the points between the two. So the one up there is 0, 2, 2, and this one we have to look for where there is a okay, because looking at it, we have 4, we have 7, That's D.
Mm-hmm.
The other one now. How can then?
Oh, do you know what you just said? You know what you just said? You said that the distance between these two is 3, right? And the distance between these two is also 3. And then this was maintained here,
Yeah.
right?
Yeah.
Now what of this one?
2, 2 is correct.
2, 2,
2.
2.
Yeah.
A structure. What is this structure? And how can we make use of it? So we're learning more about this structure. So let's continue. Mm-hmm. There's no coefficient here. It's just evaluations, right? You guys already have everything. You guys have everything already. You have all the pieces. It's just you're missing an idea that will just make everything click.
I know we're going to use the equation of the straight line.
That's another piece, okay? Equation of a straight line, yes.
I think the constant is the one you just mentioned.
Okay.
But then what's the gradient?
The gradient
The
now
gradient
is
is going to be scalar.
Wait, I think I get
The
something.
gradient should be
So you're going to pick like now when you're dealing with A,
Yes.
right? You're going to pick the point where A is just 1 and B is 0, which is 2. Right?
Uh-huh.
Multiply these 2 by that guy by 2. Multiply
Uh-huh.
2 by 2, you get 4.
Uh-huh.
Right? Look at the difference between 0 and 3.
Uh-huh.
It's just 3. You
Uh-huh.
add 3 to it, you have 7.
Uh-huh.
You have more 7.
Uh-huh.
Do the same thing for this one too. You look for the part where B is just 1
Uh-huh.
and A is 0. So I have like 3. So 3 times 3 is going to give you 9. Look at the difference between 3 and 5. So add 2 to it, you have 10.
Wait.
9, 11, 4, 7.
Wait. It says something. I think he has figured out how to do it for a very specific case, but it will translate. But it's good. You're making progress. So let me now try and explain what he said. Wait. I'm sure Rima has probably gotten it now. So 4, 7, right?
Yes.
First.
Yes.
So what are you saying?
Like now you're dealing with A first, right?
Yeah, this one is when A is evaluated at 2. Okay?
So you're going to pick the value. Yeah. You're going to pick the value where A is 1
You're going to pick the value where A is 1
and B is 0.
and B is 0.
Yes,
Okay?
that's the value.
Uh-huh.
Right? We're going to multiply whatever we have there times 2.
By what we're evaluating A
What
at.
we're evaluating at.
Uh-huh.
Right? Then we look at the difference between the value, like the difference in the top one and the down is just 3.
Uh-huh. Oh, then you get the other one.
You just add 3 to it.
Then you get the second side.
Get the second value.
Okay, so you're saying that you take this,
Yeah.
then you multiply by what A is,
Yes.
then you now add the,
Difference.
since you already know that the difference is fixed, right? So that's plus what? Plus 3, right?
Yes.
So it's going to be 2 times 2, comma, 2 times 2 plus 3. That's 4, 7. Okay, then the same way, this way, right? So how do you do it this way?
Look for the part where B is 1 and A is 0.
Where B is 1 and A is 0, that's 3.
3.
Uh-huh.
Multiply by the value you're evaluating at.
That's
3 times
3.
3 times 3.
So that's 9.
9.
So that'll be at this side.
Yes.
We're coming down now, right?
Yes.
Okay, so that will now be what? 9 plus what?
2 difference.
That's 2. That's 11.
11, yeah.
Okay. So it works. You know why it works? So it works, but you don't know why it works. Okay, now, can you do this for,
Values of like.
no, the point?
Okay, for the points.
Yes. So how can you go from 4, 7 to 13? When you know that you're evaluating at
2 points. You just
at
pick.
3.
You just pick like.
Wait, sorry. This is 0 and 1, right?
Yeah.
But this is representing B.
Yes.
Right, because I've already evaluated A. Okay, so what do we do here?
So I think you just pick the points where like A and B are both 1 1.
There's no A and B anymore, right?
Okay.
Now it's just B.
Okay, if you want to evaluate. Wait. If you want to get 13 when you're using 4 and 7, right?
Yes. And 3. And B is 3. You're trying to evaluate B at 3.
You're trying to evaluate B at 3.
Yeah.
You just pick the part where B is 1, which is 7,
Mm-hmm.
right?
Continue. So I don't 7 times 3, right?
Yes.
21. Then, what are you now going to do? But you're close.
4 plus 9.
What's 4 plus 9? Where did it come from? You just told me two numbers are so much. Huh?
I don't know, just an idea. Seeming to get a constant. So, and our constant is always at the first index. Just find
Your constant is always what?
at the first index from our representation. So, just add from 0. Just add it.
You need to explain more
I don't
precisely.
know how to explain it.
I think it just.
That's what I'm saying. That's what I
4 plus 9, where is 9 coming from?
9 is
9
like.
is 9, 11.
9
No.
You had 4 plus
No. Sorry, wait. This 4-7. This 4-7 came from a different part. And 9-11 came from a different part. You cannot use both of them together.
Yes, sir. The idea is still looking stupid. Let me just say it out. So,
In case.
I'm
No,
very
no,
stupid.
Don't worry, don't worry, I'll
This
be.
is what I'm having.
Mhm.
This is what I'm thinking.
Okay.
Now, the part between 0, and 0, 1
Yes.
is just one change.
Yes.
That is happening.
Yes.
The part between 0, 1 and 1, 1 is one change.
Yes. Eh?
But the
Yes.
between 0, 1 and 1, 1 is one change.
Yes.
But the part between 0, 0 and 1, 1 is actually the resultant of 0, 0, 0, 1 and 0,
Two
1,
changes.
1, 1. That is two changes.
Yes.
So if we are going from, if we are trying to resolve that, since the part between 0, 0 and 0, 1 is one change,
Mm-hmm.
we multiply that 3 by that 3 we are evaluating at to give us 9. And then the part between 0, 0 and 1, 1 is the resultant of 0, 0, 0, 1 and 1, 0, 1, 1, 1. So the that would be like the addition of the values there. That would be like 3, 5, then plus that 3 we are evaluating at. Something like that.
I don't really get it, but let's see. So you're saying that, what is the goal now? Are we trying to partially evaluate at
3, like
B equals 3?
B equals 3.
That's the goal.
Yes.
Okay, so how do we do that?
The part between 0, 0 and 0, 1
Yes.
is just 1.
That
One
changes.
change. So that is 3 times 3. When the part is just 1, you multiply the index of B there,
Yeah.
where B is valid,
Yeah.
by 3.
Okay, so that's 9.
That is 9.
So
So
how do you get 11?
then the part between 0, 0 and 1,
1,
1
1.
is actually 2. So because of that, we take the resultant.
Okay.
So, and we just sum it up. It just be 3, 5. Like that will be from 0 to 3 is 3, and from 3 to 5.
It's 2.
Okay,
You guys have okay.
Those are the coefficients.
Those are the evaluations.
No, there's the coefficient.
What do you mean the coefficient? The polynomial is 2a plus 3b now.
Yeah, like, and then when you're translating from 0, 0 to 0, 1, or from 1, 0 to 1, 1, that's when these come and the coefficient
0, 0 to 0, 1,
Yeah.
or what?
1, 0 to 1, 1. They are both equal to 3, which is coefficient of 3. Which is coefficient of P. And when you're doing 0, 0 to 1, 0, or 0, 1 to 1, 1, that's
It's
when
2.
A is coming out.
You're saying that the difference is the coefficient. But that's because of the way I wrote this polynomial. I could have written like 2ab. What would that mean in this scenario now? Do you get what I mean? So it could have been like 2a plus 3b plus 2ab. But it'd still be a square. So it's not like which coefficient is going to be, when there are 3 coefficients now, but there are only 2 directions. Do you get? Okay. Wait. Rohima. Do you have an idea? Not yet. Okay.
I'm looking at something. Say like at 0 to 3 is equals to 2 to 5, right?
Yes.
From 0, 0 to 0, 1 is equals to 1, 0 to 1, 1. Right? So you can say 3 minus 0, right? That 1, 0, 1 minus 0, 0 equals to 1, 1 minus 1, 0.
Are you the algebra on the Boolean vacuum?
Yeah.
It might work, actually, but I don't know if it will work. Does it always work? Okay, let me hear it. So you're saying that, let's do it. You're saying what?
So we have 0, 0.
Uh-huh.
Sorry, 0, 1 minus 1, 0.
You're doing this sort.
0, 1 minus 0, 0
Yes.
equals to 1, 1 minus 1, 0.
Okay.
0, 1 is when A is 0 and B is 1. That's 3 minus.
Abi?
No, when, that's 3B, not 3, because B is 1. Not 3B minus 0 is equals to 5AB minus 2A. That is equals to
What are we trying to do here? Are we trying to partially evaluate?
equation of the line.
Equation of which line?
The next line. 4 and 7.
Oh, of this line.
Yes.
Okay. So did you work it out?
What I'm getting doesn't 7B minus 4.
7b and minus 4.
7B
The 4 and 7 is somewhere inside. Okay. Let me put you guys out of your misery.
Thank you.
So now, the idea is that they are straight lines. Okay? So, one question I was expecting someone to ask is, okay, no, people ask it actually, but to understand, like, the next thing to understand is actually, like, why is this B, right? Why is it, like, horizontal? You know, Frank asked that question. And why is this vertical? Why is it that when the resulting thing is A, it's vertical, but when the resulting thing is B, it's horizontal? Why? Why is that the case? Just like looking at this.
Because you said it now, when you evaluate, for instance, when you evaluate something like AB,
You eliminate one
yes, it's gone, like that AB is gone, so it becomes
to reduce.
Yeah, it reduces.
But why did this not reduce to straight 4, 7? Why is it horizontal 4, 7?
So since we evaluated at A, right?
We evaluated at A.
There's a part of this cube, either horizontal or vertical, that represents A, and there's a part either
Yes.
horizontal or vertical that
Yes.
represents B.
So let's say like horizontal is one symbol
Yeah.
and vertical is one symbol. So the direction is, so you see a cube is like this, right? There are 3 directions, which is why it can represent 3 variables. A square has 2 directions, that's why it can represent 2 variables. And a line just has 1 direction, that's why it can only represent 1 variable. So if you have 5 variables, you're going to be using a structure that has like 5 different directions. Okay, but we can't see that in this case. So now the question is like, okay, the direction this so now I'm going to tell you now that this direction here is B. Is it B or A? I'm coming.
You say what?
This direction
It's B, yes.
is B.
Yes.
While this is A.
Yes.
But since we evaluated
So why?
Because this is 0, this like this OO to OB, so that it's kind of like a B line. This is 0, 0 to
Okay, I
so
saw
that's
that.
like an A line and stuff.
Also, based on what you said, right? If horizontal is B and A is vertical, when you evaluated at A equal to 2, the vertical structure collapsed. to the
Yeah,
horizontal.
but it was me that wrote this like this.
Yeah.
So I knew that that's how it would look like. So you cannot use this to now like
Justify
explain that.
No,
No,
even
no,
though, sorry, even though it's not right, we know from what you gave us.
from this?
Yes.
How can you know?
Sorry.
Why is it
How
like
do I
that?
know? I know that I'm seeing this as a point now.
Yeah.
I have Z, X, Y. You get it? So when my X is 0, I know it will be like the Y, it will flip. You know when you are plotting graph and your X is 0, what will happen? It will be on your X axis. Your Y will be on your X axis. Do you
Yeah,
get?
but
When you are plotting graph and your X is 0, your line will be on your Y axis.
Yeah.
And when you are plotting
That's
graph
what
and your
I'm
Y is 0, your line will be on your Y axis.
Meaning that if you had changed it and put 3 here and this thing here, it would have also altered the. So the other one will not be straight and the other one will be flat. So it's just like this is a kind of B line and the other one is a kind of.
so let me just explain, okay? So now we have f of a comma b, right? Right? So each of these represents a b, a b, a b, a b, right? Different values of a b, a b, a b, a b. So then this is the b line. Because a line needs an interpolating set, right? It needs the values of x with the corresponding values of y. Now, if we had chosen a, the interpolating set would have been the same, right? It would have been 0, and the other one too would have been 0. Because a is the same on both sides. That's why this cannot be like a. But then look at b. This is 0, that is 1. That's a proper interpolating set. And this is the corresponding y value. Does that make sense? So this is the b direction. If you look at the a direction, this way, then I can see this is 0 and this is 1. That's a. So the interpolating set for this line is the a0 and a1. The interpolating set for that line is also the a0 and a1. This line here. This one here and this one here. Alright? So because of this is a line, it needs an interpolating set, right? We already know that this point is 0 and this point is 2. But then this line is an f of x. So f of what should give you 0 and f of what should give you 2. It cannot be 0, 0. That the same polynomial is giving you two different values for the same point. It has to be different. So the variable that gives you that difference is the owner of that line. Does that make sense? Hmm?
I will also say because A is constant on that line.
Because if b is constant on this, a is constant on this line. No, a is not constant on this line.
Because B is constant on this line.
Then it's not the owner. Yeah, that's why it's for a. You can do it like
I
that.
now say because B is equal to 2, B is 2, B is 2, B is 2. That's why it is A line.
Yes. So let me explain. Okay. So what we're saying now is that every single line here is an equation, right? So this one now is like f1 of x. This one is f2 of x. This one is f3 of x. And this one is f4 of x, right? Right? Okay. Oh, you understand everything? Well, you know what I said, you don't understand. So let's look at this f1 of x. f1 of x has two values, right? You know it's a straight line. A straight line, you can represent a straight line with two. It's a degree 1 polynomial, right? So with 2 points, it's sufficient to represent a straight line. And we already have 2 points. So we can actually represent that as an actual straight line. So that f1 of x, if we write it at 0, what are we supposed to get?
0.
Okay, sorry. This f1 of x has 2 points, right? We don't know what. It's 0 and 3, right?
Yeah.
0 and 3. So we need to pick what the interpolating set is going to be. So what are we going to put into f that will give us 0? And what are we going to put into f that will give us 3? Right? So we can't put 0 and 0, right? That doesn't make sense. So we have to put 0 and 1. Who owns 0 and 1? B. Hence, this line is for B. Do you understand? So this f1 of this thing is for B. Hence B follows this direction. So the top one here and this one here are both for B. No, sorry. This, I mean this. And this. Does that make sense?
Yeah.
Sorry,
No,
can I start
that's
again? Yes, Michael. Begin.
No. So now see. Let me just say something. So we know that, let's say, just assume, we'll go back to it. This is for B, right? And this is for A. When we partially evaluate A, what does that mean? We're destroying A. We're destroying this straight line that is for A. That's why it's collapsed. So you're still leaving the B direction. B direction still exists. But you're partially evaluated A, so the A direction, which is this disappears. So this disappears and this disappears, leaving just something that has like this, and then you just collapse it somehow. So you're left with B. When you evaluate A, you are destroying B, right? When you evaluate B, you are destroying B. So you're going to be destroying this and this, leaving just things that, so you just collapse it. Hence why we have, does it make sense? So now so what doesn't make sense? Is it figuring out how we know who owns what line?
Yeah.
Okay. So we have a square, right? It's only for a cube, but you guys have to understand the square first before we go to the cube. So let's say this is 0, 0, 0, 1, 1, 0, 1, 1. So there are two directions here, right? We have this direction, and we have this direction, right? It doesn't have to always.
I think it's easier to visualize on a graph. 0, 0 is in the bottom left.
Firstly, maybe, yeah. But now, so 0, 0 doesn't have to be there. It could be somewhere else. But you need to know what your structure is. Okay. So let's now say we have this direction and we have this direction, right? And then we're trying to figure out which one is for A and which one is for B. Okay? So the way the simple, when you have understood it, the mental model that you will get is basically which variable changes in that direction. That's literally it. That's how I do it now. I just look at this and I'm like, okay, which variable is changing in that direction? The variable that is changing is the owner of that. Does that make sense? So like now, in this direction, it's B that's changing. Right? For both up or down. Right? A is fixed. Here, 1, 1. But B changes. And here too, A is fixed, but B changes. So that's how I know that, oh, that's for B. While this other one, look at B, 0, 0, doesn't change, but that one changes. And this other one too, 1, 1, but that other one changes. So that's how I know that that's A.
Gradients.
Hmm?
Looking like a gradient from like 0, 0 to 1, 0, 1. Yeah, like 8, 0.
Mm-hmm. Yes. A is fixed, 0. Then B is just changing. Does it make sense? Does it make sense how to like know the direction?
Yeah.
That makes sense, right?
Yeah.
You sure? Are we good? It is dense. The implementation is straightforward once you have internalized the theory. So now it's the internalization of the theory that we have to do. So if anything is not clear, let's just... Okay, so now, let's now look at evaluation on this structure. Okay? So if I want to evaluate 0, 0, we'll just look at the value at 0, 0, right? Right?
Yeah.
0, 0 is just 0. If I want to evaluate at 0, 1, that's just 3. If I want to evaluate at 1, 0, that's just 2. If I want to evaluate at 1, 1, that's just 5. Now the question is, how do we evaluate when it's not on the shape? Okay? So let's now draw a bigger graph. Let's do something like this. This is 0, 0, right? Let's just do this 0, and let's say this is 1, and this is also 1, right? And so that means that this point here, let's now draw the cube. This is what, 0, 0, right? And this one is what? So let's assume this is A. No, this is B. Let's say this is B, right? And let's say this is A, right? Based on what we just did so far. So this is 0, 0, then this is what? 0, 1. Right? Remember that B owns this line, so we only have to change B, right? And then this one is going to be what? Right? So this is what we have. This is what we have so far. And then this is what? 0, 3, 2, 5. This is what it looks like. So if you want to evaluate 0, 0, you just look it up, right? 0, 0, 1, 1, 0, 1, 1. Are fine? Now let's want to evaluate 2, 3. So 2, 3, let's say this is 2, this is 2, this is 3, this is 3, right? If I'm evaluating at 2, 3, A is what? 2, B is what? So we need to look for 2 on A, which is this, right? And for 3 on B, which is this, right? So that means that point is going to be somewhere here. So the question is, given this, can we figure out what the value of that will be? Yes. You have to extend. She said you have to extend. So what are you extending? Exactly. So what Rima just said now is that if we know the equation of this line, then we can evaluate that line at 3. You get? And if we know the equation of, let's say, this line, we can evaluate it at any other point. So how you do this now is that there are 2 ways to go about this. You could first of all partially evaluate. So okay, let's now look at partial evaluation first. Okay? It's getting there. So let's say we want to partially evaluate A at 2. What would that look like? A equals 2. So it will be something. So it's just going to be. That's what A equals 2 is going to be. Right? So this point here is going to be, I think, 4 and 7. Wait, how? Yes, 4 and 7. Yes. This 4 and 7 is the equivalent of all those 0, 3, 2, 5. Okay? So the question now is, how can we get 4 by extending, let's say, this 2? And how can we get 7 by extending? You understand? Is it making sense a bit?
Let's try another one because if you're using 2 now, you can say 2 plus 2 or 2 times 2.
What do you mean?
So let's try 3 or something else.
So if I'm evaluating at 3, we're going to have something here and something here. I don't know what those values are. But we can know what the values are. 6 and 9.
Yeah, actually 6 and 9.
You're adding like
2 times 3 and then 6 plus 9. Sorry, 6 plus 3.
So let me just. So let's just talk about that extension, right? Let's talk about the extension. So this represents a straight line, right?
Yeah.
That you can evaluate at any point. We already said that this straight line, if you evaluate at 0, you get what? 0. And if you evaluate at 1, you get 2. So you already have enough to interpolate that straight line, right? You have 2 points. A line is a degree 1 polynomial, and you already have 2 points, 0, 0, and 1, 2. So if you interpolate this, you're going to get a formula that you can now evaluate at any. Yes. So if you wanted to get 3, we evaluate at 3, and we know what this value is. Then for this other one, we'll need to now do this other guy here, right? So 0, 3 and 1, 5. Interpolate that, you get a polynomial for this line, this extension. Then evaluate that at 3, and you now get the value of this point. Now that you have that, you now have a new straight line. So remember that time I was saying, like, let's go back to the 2,3, just to make it easier. So we wanted to evaluate at 2,3, right? The goal is here, right? Here. So to get this, we need to either get something here or something here. Because let's say we have 2 points here, we can interpolate this and then evaluate at anything here. And if we have 2 points here, we can interpolate this and evaluate at anything here. So that's the difference between the partial evaluation at B and the partial evaluation at A. That's why they looked different. So let's say we wanted to go from this. So what we'll first of all do is we interpolate those two. We'll get a polynomial. We'll evaluate that polynomial at what? At 2. So we get a value. The value is going to be 4. We already know. We'll do an example. But the value is going to be 4. Then we interpolate that 3, 5 also, right? To get the equation of that line. We evaluate that at 2 to get a new point called what? 7. So now we also have 2 points that describes another straight line. So now this straight line is the extent, is this other straight line, right? Yeah. But we already know the 2 part of it. So I've done the A part. So all we need to do is just evaluate this at 3. Does that make sense? We interpolate this, we get the equation of this line, and then we evaluate this line at 3. And then we have gotten 2,3. Does it make sense?
Yeah.
It's very dense.
So how are we going to evaluate 4, 7 as 3?
So 4, 7 represents f of x.
Yes.
They just make x 3. Right? Yeah.
Does it make sense that we are having 2 different line equations for both?
There are 2 different lines.
2 different.
There are 2 different lines.
Equation for the 2 of them.
Yeah, there are 2 different lines.
Because if we take the 2 different line equations, then we definitely arrive at 4 and 7.
Yes. And there are 2 different lines because if you look at the outputs, it's like 0 and 2 and then 3 and 5.
Yeah.
So one of the line evaluates to 3 when you evaluate at 0.
Yes.
And it evaluates to 5 when you evaluate at 1.
Yeah.
But the other one evaluates to 0 when you evaluate at 0. And it evaluates to 2 when you evaluate at 1.
Because what I asked was, in my head I was just doing something like, the equation of a line is ax plus b.
Yes.
And if we take this first one,
Yes.
where x is 0,
Yeah.
then ax plus b would be just b. When f is 0, then where x is 0, then where x is
1. It will be a plus b.
That would be a plus b.
Yes.
And then
Should we do an example?
Yes.
Like, let's do a proper example. But does anyone have any question about this so far? Or you have questions but you don't know? Okay, a question here.
I thought the reason we're trying to like examine the shape and how it relates to the value was that we don't want to like interpolate, get back to the function
Yes.
and then start evaluating again.
Yeah. But we're still interpolating, right?
Yeah.
Yes. But this interpolation is very cheap. It's just straight line interpolation. In fact, there is a formula that we'll get to that allows you to interpolate and evaluate simultaneously. And it's very, very cheap. Like very, very, very cheap. Just like a couple multiplications and 1 addition. So let's do a concrete example. Okay, Francis has something.
Let me ask one question. Right. There are 2 ways to go from that point is 2, 3. Do we agree that there are 2 ways?
Yeah.
Okay, he has shown the first way. I don't know if he showed the second way. So what is going to be the second way?
Diagonal.
No.
This way. And
You said there are 2 ways to get to.
There are 2 ways to get to 2, 3.
Yeah.
Right? The first way is you evaluate the line, the A line, right? 0 and 2. That line is
It's talking
0 and
about
2, right?
this
You
one
evaluate it at 2.
okay.
to get
4.
Yeah.
And you also evaluate the line 3, 5
Yeah.
to get 7.
Yeah.
And then you got a new line, right?
Yeah.
Then you now evaluate that line at 3 to get 2, 3.
that's one way, right?
That's one way. Right?
Yeah.
Do we agree that that's one way to get to 2,
Yeah.
3? So what is the second way?
Evaluate
Yeah.
the
Yeah.
zero.
Yeah.
Then you evaluate
Yeah.
Then you evaluate at 3.
Okay.
Then 1, 3. Then the other one, yes. And then you talk.
So that was 9 and
And then
11.
you evaluate.
That was 9 and 11.
That was 9 and 11. So that answer was 9 and 11.
That's what I just said.
You just said. So this one is 4, 7. That one is 9, 11. By the end of the day, regardless of the one you use, you will get back 13. Maybe. You want to see like that. So it's more like 2 dimension to 1 dimension. Then 1 dimension to a point, to 0D. And likewise, 2 dimensions to 1D, and then 1D to 0D. You guys will have to watch this or ask more questions, because this is not, it's not supposed to be straightforward at all. You cannot just learn it in a couple hours. It's not even possible. You can't learn it in a couple hours. Huh?
What is moving fast?
You have to take your time and really. Is there a particular?
Wisdom.
It's not wisdom's algorithm. No. Like Aquax, for example, right? The library. They had a polynomial. They had this evaluation from each thing. So we're looking at how they implemented their partial evaluate. And we're like, what is this? Right? So what we saw the end result of everything. And we're like, what's this? So we're just looking at it for, like, I was trying to read a paper. And I was supposed to read it in a short period of time. But just that line took me like more than a week. Just to understand that one line. So in order to understand that one line, we had to go and understand like what Boolean hypercubes are. Then when we understood what Boolean hypercubes are, like all this is that we're talking about now, we had to rediscover it. It's not like there's a material that you go and look at it like, oh, there's materials, there are probably materials, maybe in math, that we're not aware of. But we had like the starting point, which is like Boolean hypercubes. And we had the ending point, which is how they did their partial evaluation. And then we had to figure out everything in the middle before we could even use that formula. So we're on that for like weeks just to understand that. So what we're now doing is like we're just like trying to show you the full thing. You don't need to understand everything immediately. Because of when you see, there'll get to a point where you can abstract away. Like I don't think about all this too much anymore, right? Because I've abstracted away the core knowledge I need to actually like do like implementation and stuff. So I don't need to think about it too deeply. But for now, just like take it all in, then you manipulate it a bit. She has an announcement for you guys.
We don't want.
Good morning. Nah, I'm not doing. People should calm down for me. Do like this. I want my phone. Hi, good morning. So So please, we're going to be. I want you guys to help me with the content. Sorry, I have to take content. I'm very tall. I want to actually take content with you guys and Mr. Israel. So I don't know. I don't know if you guys do social media or maybe like this time it's okay. But the content is somewhere. He just has to like you guys say something to him and he like tries to guess who's speaking with the like recognize your voice. He's not seen and we need I think he has like you guys like bond a lot. So I need you guys to help me. It's going to happen by 1. I already took like permission from our mentor. So please when it's time for your
No. Wait, how long is it going to take?
It's going to take not much 20 minutes now.
Are you sure?
Are you sure?
Yes, I'm very sure.
You can take your time.
Like,
10 minutes. 20
your
minutes.
mentor says 20 minutes max. So work with 20 minutes. So please, once it's one, do not, please, I'm begging you, please do not leave the class.
Is it outside?
Yeah.
They're still after class.
What time is after?
Don't worry, after 3.
I think Mr. Israel. Okay, if it's 3, I have to go and speak to Mr. Israel and I'll come back and.
Oh yeah, okay. Then
We love it too.
My friend.
Okay, that's an example. So I'll do an example the way we think about it now, right? Yes. It's not going to be hard, don't worry. So 0, 0, 0, 0, 1, 1, 0, 1, 1, right? 0, 3, 2, 5. Cool?
Yeah.
We want to partially evaluate at A, right? A is going to be equal to 2. So we need to find the line for A, right? We need to find the line for A and evaluate it at 2.
Yeah.
Cool?
Yeah.
To find a line, we need 2 points. Cool?
Yeah.
So we need to find the 2 points that will give us the A line. What does that mean? We need to find 2 points that A is different, but B is the same. No. We're trying to find something that can evaluate A. Right? So we need A to be changing, right? No. We want to evaluate A. In order to evaluate A cannot, like, how do I put it? So sorry, wait. Let me explain this. For you to evaluate A, you need 2 different points of A. So you can get a line for A. Like when you have 2 different points of A, you can get a straight line for A. And you can evaluate that straight line at any other point. So you know the goal is to evaluate A at 2. So we need to get 2 different points for A, get a straight line, then evaluate that straight line at 2. Does that make sense?
One it is.
Okay, 3 p.m. works, but please let's not do the class. So I don't go around.
Alright. Okay. Okay, so let's continue now. I don't know, should I do the interpolate evaluate function first or just... No, let's just use intuition for now. Yeah. So AB, right? Right? Yeah?
The class doesn't end 3 p.m.
Yes.
Not 2.
No.
Don't waste time.
So AB, right? Are we following?
Yes.
So we're trying to find 2 points. You know, A has 2 straight lines. So we're going to find those 2 straight lines so that we can evaluate it at 2. Cool? So where does A change but B does not change?
3 and 5.
At 0 and 2. The first.
So she said 3 and 5.
3 and 5.
0 and 9.
Yes. Yes, and also 0 and 2.
Do you see that?
Sorry, come again with that. So where does A change but B doesn't change?
Yes. So whenever you want to partially evaluate at a variable, you need to find where that variable changes so that you can have 2 different values for that variable. Because if you don't have 2 different values for the variable, you can never get more values for that variable. So you need to find where that variable changes, but then the other one does not change. So we have 2 such cases. The first one is 0, 0 and 1, 0, right? So A is changing here. I need to write this in on the tab because people that will watch. A is changing here, but B is fixed in both cases. So that means that these 2 values, 0 and 2, are on one of those lines for A. And if we check back, you can see that these were the lines for A. And you can see 0 and 2 is there. So this is like another way to kind of like get this diagrammatic. Then B, then there's another one again, right? Like this one and this one, right? A is changing, but B is fixed. B is 1, 1, and A is 0, 1. So that's what 3 and 5, right? And if you look at this again, you see like 3 and 5. So by just looking at the Boolean hypercube, we can know the pairs that are for A. Are we making sense? We should go by it again. Okay. So the goal is partially evaluate at A equals 2, right? To do that, we need to get straight lines for A, right? To get a straight line for A, we need where the value of A is different. Okay? So the value of A is different at the point where A is different. Okay? But then B must be fixed, right? Because we're not partially evaluating at B. Like you need to leave B alone. A, so let's say in this case B is 0, right? You are going to find the other thing that has B as 0, but A will now be different in that case. You get? So that's this one. And what? So that means that this 0 and 2 are on one straight line. And that straight line is one of the A's straight line. Okay? Now we'll find another straight line that has the same property. Because we have 4 points. So this one now, B is 1 here. B is also 1 here. So good, B doesn't change. But A is changing, which is what we want. So that means 3 and 5 are on another straight line. But that's also A's straight line. So now we have the 2 points that we care about. So what we need to do now is interpolate those points and then evaluate it at A. Right? Let's proceed. So now we call this pairing. We pair the labels. So we pair 0, 0 with what? 1, 0. Right? And then we pair 0, 1 with what? So this is the pairing. And each of these pairing has their equivalent y points. So what's the y point for 0, 0?
Yeah.
What's the y point for 1, 0? 1, 0.
Oh, 2.
Yes. What's the 0, 1? 1, 1. So now these 2 represent straight lines for A. Okay? So what we need to do now is get the actual straight line. And get the actual straight line. Then evaluate it at 2. Fine? So we do regular Lagrange interpolation. There's a faster way to do it, a way faster way, but we'll do regular Lagrange interpolation for now. Okay? So what's this? Let's get this one first. The points are what?
0.
Right? A is different, right? And it's just A or caring about. So we just look at A. 0, 0, 1, 2. Does that make sense?
But you wrote 0, 1.
Sorry, that was my bad. Make sense?
Yeah.
So this is the point we're interpolating. So now we just interpolate this point, right? So it's like the output times L0 plus the other output times L. Does it make sense? Right? So we could do the multilinear way we did yesterday. Because the interpolating set is still 0, 1. So we already had that check 0, check 1. We could use that here. Or we could also use regular Lagrange interpolation. Which one will be less confusing? Okay. So we don't care about this, right?
Yeah.
So this is just like 2 times check 1, right?
And that's just the 0.
Which is A in this case. So this first line is 2A. So this line here is 2A. And it makes sense, right? If I write at 0, what is it?
Yeah.
If I write at 1, what is it? Does it make sense? Now I can evaluate it anywhere. That's the extension. So we got this 2A, and 2A represents the entire thing on this, like anywhere here.
Yeah.
So I can evaluate at any point here. You get? So now if I evaluate at 2, you can see where we got at 4. But let's get the second one first. So this is 3 times what? L0 of x, right?
Yeah.
Plus 5 times L1 of x.
Yeah.
So that's, right?
Yeah.
So L0 is what? 1 minus 5 times what? That's 3, which is what? So this is the second line. If I write at 0, what is that? 3. If I write at 1, what is that? 5. If I write at 1, right? 3 plus 2A. Yes. Are we good? Good? So what we're saying now is that this line here is 2A, while this line here is 3 plus 2A. Make sense?
Yeah, makes sense actually.
Now that we have these lines, we can now get these points here. Right? So since we're evaluating A, partially evaluating A at 2, we just evaluate 2A at 2. What's that? That's how we got this. And then 3 plus 2 times 2, 3 plus 4, which is equal to 7. That's how we get this point here. Does it make sense? You sure? So, so the way we do it is, we now create a new evaluation array. You know, it's a 0, 0, 0, 1, 1, 0, 1, 1. Since we have removed one variable, so it'll be 0, 1, right? So you get the new index from the index of B. So what's the index of B in this one? 0, right? What's the index of B in this one? So whatever we get when we evaluate this at 2 will be what will be at 0. Right? Okay. So, you know we started with a square, which is 0, 0, 0, 1, 1, 0, 1, 1. When we evaluate A, we're going to get a line, right? Which is just 0 and 1. So, what we first thought did was that we paired up each element in this, right? Right? So we paired up each element in this to get this one and this one. So we got 2A and we got 3 plus 2A. Then the next thing is to evaluate both of them at 2. But then when we're done, we need to store the result in a new evaluation form representation of a polynomial. Okay? And that new representation is just going to be 0, 1, since it's just like a single variable. But I've gotten rid of a. So my question is like, when you evaluate 2a at 2 is 4, right? When you evaluate this one at 2 is 7. I can write 7 here and write 4 here. I can write 4 here and write 7 here. Alright? So what I'm trying to tell you is like how you will know what position to put them in. So the position is based on the position of B. So B here is always 0. So 2a is associated with 0. And B here is always 1. So 3 plus 2a is associated with this. So that means that 4 is going to go here and 7 is going to go here. Does that make sense?
Yes.
Make sense? Now we take this. There's no pairing to do here again. So now it's B, right? We need where B is different, but the rest of them are the same. That's how we pair things up, right?
Yeah.
The first one, we looked at where A is different, but B is the same. In this case, we're looking for where B is different, but everything is the same. But there's no other thing, right? So we just pair these two up. Okay? So we'll create a straight line from this, and we evaluate at B. What was B supposed to be? 3. Right? We're evaluating it at 2, 3. So A, B. This is the evaluation at 2. They want to get the evaluation at 3. So to get that, we need to draw a straight line between these two, which is what we're going to do the same thing now. So that's what? 4 times L, right? Right? So that's 4. Now we're working in terms of B, right?
Yeah.
So this is 1 minus B.
Plus 7b.
It's always the same. Like, it's always like this. The formula is always like this. It's always L0, L1. You're always using 2 points to construct a straight line. It's always going to be like this. That's like a hint to the optimization. You get it? So this is now what? 4 minus 4b plus 7b, right? Which is what?
4 plus 3b.
So now this is this line here. So we can evaluate it anywhere. Okay. I remember that our goal was. So we're evaluating it at 3. Evaluate at 3, that's what? 4 plus 9.
9, 11. 13, sorry.
I remember that we got 13 at one point. I passed it.
Yeah.
Yeah. So we got 4, 7 because we partially evaluated at A first. Then we now partially evaluated at B to get 13. Let's do the reverse. Let's partially evaluate at B first, then evaluate at A. So B will be equal to 3, then A will be equal to 2. So let's do the reverse. So we're expecting 9, 11, then 13. So let's do that. Zero, 3, 2, 5. You guys should follow this. So we're looking for where B is different. Yes. So our partial evaluation at B equals what? 3. We're looking for where B is different, but A is the same. I want to pair them up like that. So which one?
0, 0, 0, 1.
So 0, 0, 0, 1 and 1, 0, 1, 1. What is 0, 0? So then we interpolate this, right? So that'll be 0 times L0 of x plus 3 times L1 of x. We're getting a B polynomial now, right?
Yeah.
So this is going to be, we don't care about this other one. So that'll be 3. So easy. Then this other one is going to be 0 times,
10. I'm
sorry,
sorry, 2.
2. Yes, L1. No. So, it's B. Yeah. 1, 1 is don't care about that. So that's what? 2 times what? 1 minus B.
Plus 5. 2 minus 2b plus 5. Plus 3.
So now we have the 2. So what's
Is
also
that 3 or 2?
3.
good? Now we're supposed to evaluate them as what? B equals 3, right? So 3b evaluated at 3 is what?
9.
And then 2 plus 3 times 3, right? 11. So how do we know where to put what?
We find
Where a is the same, right? So for this one now, a was what? 0. So I'm going to put the result of 3b in 0, which is what? 9. And then 1 is just going to take the other one. So when we evaluate this at b equals 3, we get 9, 11. But we did it through like the evaluation form directly. You know, you could have interpolated and then evaluated and then gone back. But we did it straight away by just understanding the structure of the Boolean hypercube. So let's now do 9, 11.
Can you just go back how you determined where now we do?
Okay. So you know, you look at where b is so in this case now, you know b is what we're evaluating. So you just look at where a is. The constant one, you just pick its value. So like you know b is different. That was the original goal. So just look at what a is. A is 0 here, and a is also 0 here. So that means the result of this interpolation and evaluation will go to 0.
Because they are both the same. Because they are both 0.
Because they are both the same.
The second one, they are also the same.
Yes. So that's why it will go to 1. No, sorry, because they are both 0, that's why it will go to 0. And because they are both 1, that's why it will go to 1. But it has to be the same. So now let's do 9, 11. 9, 11, right? We're evaluating at a equals to what? 2, right?
Yeah.
There's nothing to pair, it's already 2, right? So it's just like 9 times L0 of x plus 11 times L1 of x, which is what? 9 times 1 minus a this time, plus 11 times what? A. That's 9 minus 9a plus 11a, right? 9 minus, no, plus, right? My 9 looks like a. 9 plus 2a, right? Then what were we evaluating it at? 2. So that's like 9 plus 4, which is equal to. Does it make sense?
Ah.
Eh?
Partial.
Yeah. So like if you could the full evaluation you did it via multiple partial evaluations.
Can you show your
Yeah, I can show you the notes. Yeah, I can show you the notes.
more to understand the more stress?
Yeah.
Not implementation.
We'll do an implementation design session too. But is it making sense? Half sense. Okay, yeah. Do you guys want to try something by yourselves? Yes. Yes. So do this. F of a comma b, yes, now is equal to. No, I'm trying to get the evaluation form. You don't need to write this one. 3ab plus 2b, right? So this 0, 0, 0, 1, 1, 0, 1, 1, right? 0, 0 is what? 0. 0, 1 is 2. 1, 0 is 1, 1 is. Okay. So this is your evaluation area. You're given a polynomial 0, 2, 0, 5. Evaluate a at 5. So you should have a new array that has just 2 elements inside. That's it. So evaluate a at 5.
Just
Yeah, just a. So you're not getting a point. This is enough.
Can you like all go to when you solve for others?
for the first one. That means you do 2. Yes.
Michael.
Yeah, it's fine, it's fine.
What is the question?
This is better, right?
We need the question.
Okay, let me. Oh, God,
We
man.
need the question. Write the question down.
So I'll wrap the question in red. This is the question. Okay? Then this is good, right?
Yeah, that's good. Thank you.
Then when everybody is done, open.
So you get 5B and 2 minus 2.
You can try it against the original.
How you evaluating for
Sorry.
Right. 3A plus 2B. 3AB plus 2B. So then you can test against A equals 5.
0, 0, okay, 0, 0 is 0. Okay, the one that this is changed. Both of them are changed.
So my own mind is like you don't partially for me because 17 and 0.
Yes,
17 and 0. So I'm now like do partial evaluation on partial evaluation. Special. So how do I feel? How do I would like start it from this one.
Okay, so just if you look at so A is different, right? But B is the same.
So one is
So this is 111, there's no one.
yes, that's it.
I didn't consider these zeros.
Because of the
I didn't solve for the any of these ones.
that one they're still starting. They are partially evaluating the base. So yeah.
Which is the inverse of what we did here.
Because they were starting.
I just don't know if it's
That was what we did now. That's it. 0, 1, 1. How did I not get right?
All right.
This for sure.
When you got it down to a point,
And it's like a shortcut.
rather than doing interpolating.
So the more you just code the show,
Was the old one? Yes. No, that one was more like the dense and the sparse. So not even taking the evaluation whatsoever. This one is short. To understand, yes. But once you understand it, it's not tricky again.
oh, this is all of it.
Yeah,
There's more.
no, this is all of it. This is all of it. Okay. So that's. Let us try it now. Okay, most people already know it. Let's try it. I'm going to just do it once. Hold on a second. I want to do it now. So A equals 5, right? Once partially evaluate at A. So we need to look at the places that A is different and pair them up. Okay? So I'm just going to write out the Boolean hypercube just so that I can know the indices. So this is 0, 0, 0, 1, 1, 0, 1, 1, right? So we're looking for where A is different but B is the same. Okay? So that's 0, 0 and 1, 0, right? So we're going to pair these two up. Then we're also going to pair this 2 up. So 0, 0, 1, 0, that's 0 and 0, right? And then 0, 1, 1, 1, that's 2 and 5. So it's going to be 0 times L0 of x plus 0 times L1 of x. 0 times 0, so everything will be 0, right? Then where is this going to stay in my new array? Yes. So I'm going to have to put these results in a new array. That array is going to collect its index from the one that is constant, which is b in this case. Do you get? You know, A was different, but B was the same. That B that was the same, that's what we're going to put the answer. Do you understand? Yeah, so we have solved this one, and we got 0. We're also going to solve this one, and we'll get something else. But now you can see that this one, B is 1. So we'll put the answer at 1 in the new array. I need to actually do this for something larger. I don't know if this is enough, but we'll see. So this will be what? 2. One minus A. Then we're advising that A equals 5, right? Right? But see that B is at what? 1. So it's sufficient to just put it at. Do you understand? So 0, 2, 0, 5, partially evaluated at A equals 2, will give you this. Thank you. Does it make sense?
You said where 0 and 0 are constant, that's what you put the second dot.
Yes. Where?
Constant in the second side.
Where what? Sorry.
0 are constant. That's what you put the first result. Like that way you go equals to 0.
Yes. So, you know, A is anything that is different. So the other thing is where you put the result in. So in the first case, right, B is 0, right? So you put the result of that in the 0 index of the array. Why in this case, 1, I don't know if you get what I mean. You do not. So like, every time you partially evaluate, you reduce the size of the array by half. That makes sense, right? And you do that because of you pair stuff up. And then you now get a new value for each pair. So you now need to figure out where do I put that value for a particular pair, right? So you get that pair index from the constant index, or from the constant value in the pairing. So in this case now, the pairing is 0, 0, and 1, 0. If you look at the A side, they are different, right? But if you look at the B side, they're the same. So that B value is where you put the result of that in the new array. So like the B value is 0, right? So then we're going to put whatever we get there at index 0.
The B value is 0.
Yeah.
So you now put.
So you put the result of the
What index?
at 0.
At index 0.
Yes.
You know, I was thinking you meant since it's B, you at the other index. That's what I was thinking for like
At which other index?
A.
So after we have evaluated, there's no concept of A anymore. In the sense that we have reduced the polynomial to a smaller degree, not smaller, less variables, right? One less variables. But I don't know if I get your questions correctly. So this is 0 and 1, right? We're putting 17 at 1 because of the pairing for 17 had 1 as the thing that is not changing. Yes. That's why I put it at 1. Why this one? The thing that is not changing is 0. That's why I put it at 0. But we need to do it for 3. I need to confirm whether the logic translates. But does it make sense? Does it make sense? So that's, we'll do it now. We'll try it.
Can you reiterate what you explained?
So I was saying that you pair, right?
Yeah.
So when you pair, you linear interpolate and evaluate, right? So you get the new values, that's 0 and 17. So the question now is how do I know where to put it in the new array? So you put in the new array based on the things that didn't change.
So you interpolated the so like I'm still using the graphical. I don't really understand this. So I'm using the graphical. So the one where we took a like a vertical A lines where we had 0 and 0. So you interpolated for that, and that was all the reason. So you did for 2 and 5.
This, right?
Yes.
Yes.
So you did for 0 and
Yes.
so if we were to draw it, we're going to have 0, 0, and 2, 5. Like as the A.
Why 0, 0 and 2, 5? Where's
Like
2?
if you that pairing that you did.
Yeah, 0, 2 and 3, 5, right?
Yeah.
Okay, you're not looking at the other diagram, right? For the new.
Yes, for the new.
Okay. Oh, okay. So that's I don't know how to draw. This will be 0 here, right? Then 0 here, then 2 here, then 5 here, right?
Yeah.
Okay, yeah. So you have this, yes.
Yeah. So the one for the 0, 0 gives 0.
Yes.
While the one for the 2, 5 gives 7.
And we're evaluating at 5, right? So let's say this is 0, this is 1. Then let's say somewhere along the line there's 5 here.
5, yeah.
So when you evaluate this is 0.
Yeah.
And when you evaluate this is 17. So you now have a line that looks like this.
Yeah.
Yeah.
I get it.
Then can I use this line to get anything here? Anything along this dimension. So let's do for 3. I need to know how it works with 3. Yeah.
Before you go to 3,
Yeah.
could you for one last time explain how, like, basically why we can cipher that, like, when we want to evaluate for A, we have to, like, find the points where
A is different.
Like, for one last time, please.
Okay. The reason is because all of these points here, from these 4 points,
Yeah.
we can get 4 straight lines,
Sure.
right?
Yeah.
But only 2 are in the A direction, right? Only 2 are in the A direction. So we need to get the one that is in the A's direction. So since it's in the A's direction, that means that A is changing. Do you get what I mean? So like, let me use this graph again. So this is A's direction, right? This is A's direction, right?
Yeah.
So you need to, you can see that A is changing, like one of the value will be here and one of the value is here. But since it's on this A line, then one value will be at 0 and one value will be at 1. But we're still on the same B. Like if you look at this B now, right? This is the B. Both values are still on the same B point. I don't know if that makes sense. Like this line represents B, right? Then both points here are still on the same B point. So that's why B has to be the same. And then A is different, so you can get the top and the bottom. You get?
Yeah.
And the other one is like the other one too, B is fixed at 1. But then you can get 2 points if you traverse up and down. So the up down traversal is you saying A is 0 and A is 1, but B is 1. So you saying B1 is like I want something on this line. You saying B is 0, it means I want something on this other line. Then when A is 0, you're picking it in at the top. When A is 1, you're picking it in at the bottom. Does it make sense?
Yeah.
Thanks.
Answers are putting your values directly to the value of it, directly to the
17b. Wait, that's the original equation, right? Yes. You did coefficient form, right? You're talking about coefficient form. Yeah.
You have to like go ahead and like check for another value. I would like just like
To be like, what do you mean another value?
to a point.
Yeah, to a point, yes. So you can now go anywhere by evaluating that 17b at b, at any value of b.
And would you do that?
So you want to get a point. Okay. At any b. So we went from, what was this polynomial again?
Huh?
What was this original polynomial? 3ab. Okay. So this one here is 3ab plus 2b. Okay. And then this one is going to be, I don't know actually. Man, I don't care because I don't do coefficient form anymore.
Okay, so that one does not like.
I don't
It's not
get-
like we know that the first place is A and the second place is B, so we don't really know what it is.
What do you mean?
Like you know, the one above now, like
Three.
we just say no, when we interpolate normally,
Yeah.
we just say the first like for univariate,
Yeah.
we just say the first one is constant, second one is
Yeah.
plus.
No,
So this one now
no.
does
Yeah,
not
no.
really-
It's just evaluations over the Boolean hypercube. But there's structure. The first one is 0, 0, depends on the number of variables. If you have two variables, the first one is 0, 0. Then the second one is 0, 1. The next one is 1, 0. But if you have three variables, that's 0, 0, 0, 0, 0, 1,
Yes.
on and on like that.
Yes.
So the structure,
Yeah. So I'm not talking of when we now get the 0, 17 for instance.
yeah,
Does that structure pass down?
yes,
or-
but now in a lower dimension. So now it's just one variable, right? So this one is just 0, 1. You get? So the other one was 0, 0, 0, 1, 1, 0, 1, 1. This one is just 0, 1. And then when you,
this is 17b, does it make sense?
I don't know. I think it is. I think it does. But the only way I'll be able to know is by like interpolating. But it is definitely 17b
Sorry,
because constant is 0.
I want to think about that diagram that you drew.
Okay.
The one that you drew, like the last time I asked you for. Yeah, and this. So when we got 0 and 17, I just want to know why we stopped. So if we had like the
Value of b.
if we had like the b value,
Yeah.
what would have done next to that to interpolate that 0 and
17. Yes.
Then that will give us
A
the value
polynomial.
of that line.
Yeah.
Then we can now
Evaluate it anywhere along that line, which is what he asked me to do now. You good? So now we evaluated a at 5, right?
Yeah.
So a is 5. Now also wanted to evaluate b at 2. Also, okay. So when we evaluated a at 5, we went from 0 to 0, 5, right? To what? 0, 17. So all we need to do is just evaluate this at 2. Cool? So what we do is, where is b difference? It's just 2 points. So you can just pair it immediately, right? Because technically this is like 0, 1. So it's different already. So just pair it up. So that'll be 0 times L0 of x plus 17 times L1 of x. Which is what? 0 times, it doesn't matter actually. So that's 17 times b. So yeah, right, it's 17b. So once you have this, you can now evaluate it at 2. So that'll be 17 times 2, which is what? So now we can test, sorry. We can test whether this is correct by evaluating the original polynomial at 5 and 2, right? Which is what? 3ab plus what?
Plus 2b.
Oh. So we're evaluating it at what? A is 5, right? B is 2.
Yes, it's 34.
So this is 15 times 2, which is 30, right? And 30 plus 4. Does it make sense? And then you can see this graphically also, right? For people that prefer the graphical representation.
yeah.
So you have 4 points, right? And then this is 0, 0, 0, 1, 1, 0, 1, 1, right? What's that? 0, 2, 0, 5. So this is 0, this is 2, this is 0, this is 5, right? So we're partially evaluating what? A. So we're looking at where A is different, which is like this direction, okay? So that means we pair these 2 points up, which makes sense, right? Because we're going in this direction. And then we interpolate it, and then we get the evaluation at 5. So let's say this is like 0, 1, 2, 3, 4, 5. So we're getting this point here, right? And this point here is what? 0, right? So that's fine. Then we'll do the same thing here. So we're going to interpolate and get the same point. That will be what? 17, right? So this is like 0, 17. Then now we're supposed to evaluate at 2, right? On B. So you can see that A has been collapsed somehow. Before we had like 2 entries for A. But after we evaluate, we now have just 1 entry for A. But we still have 2 entries for B. That means B is still undefined. When you have like, and you know a straight line, if you have 2 points, you can get any other points. So once you have 2 points, it means that you have not like fixed it. It's still, you can pick. But now that we have picked something for A, there's only 1 entry. So you cannot like pick another point again, right? It has already disappeared. It's like, it's fixed. So now that it's fixed, but you can see that B is still not fixed. We still have 2 things for B.
One of them was 0.
What do you mean by 0? One of them will be collapsed. Is that what you mean? Yes, every time you partially evaluate, it collapses. So now that we still have something along the B axis, we can just stretch it to any point that we want. So let's say we wanted to evaluate at what? What was B? B was 2, right?
Yes.
So this is 0. This is 0. This is 1. And let's say this is 2. So we just stretch it. And then we find like the 2 value here, which is going to be what? S4. And that's how we get S4. And we can do it in 2 ways, right? You know, we went down. We could have partially evaluated B first. So we'll have gone this way. We'll evaluate at 2. We'll have gone this way. We'll evaluate at 2. So now you can see that B has been fixed. Like it's only like here now. We don't have 2 for B anymore. So we cannot. But you can see that A is still. So it's undefined, meaning that we can still stretch it. So then when we stretch it, we can stretch it to this point. And we'll get exactly the same 34. So the direction doesn't matter, you get the same value. Does it make sense? So choose the one that works for you. Graphical or it's the same thing. It's the same thing, just different ways of seeing the same thing. It's the same thing. Like me, I also prefer this. Like just for the intuition. To know what is happening behind the scenes.
I'm not going to write a program that now does exactly like this.
Relax first.
No, like, I'm not saying now. I'm saying, like, are we supposed to? No, I don't want to do it next week.
You guys are supposed to do it today,
No, like,
but it's still confusing. So we'll start tomorrow. But the idea was that you guys do it today, but I can see that it is very, very dense. Yeah. So you guys need some time to make it fast. You guys need some time to make it fast, exactly. Yeah. Then you now come on. So we'll do it tomorrow. Alright. But let's now do more examples, just so that it can. More? You want to write it? Okay. You'll be fine.
So with this solution, I mean that we don't essentially make diagrams or FFT. So I can save my space for the
No. FFT is for univariate.
yes, like that one for
yes.
But for this one now,
you don't even need interpolation. Like that's so cool, right? Like you just have the points. It's so cool. So you just have the points and then you don't need to interpolate. So let's do some more examples now. Now with two. No, the thing is, I can't promise that. I want to say to get easier, but I cannot promise that. I can't promise that actually.
Will you ever get easier when you get
Maybe. Eh?
I think right now, I'm making more research on this stuff. I think it's easy.
We still read papers and papers take a long time to understand. No, not if you want to. Those are examples. Oh, it's clear. I want to do for 3. I really want to do for 3. I don't know if 3 will work. Huh? No, just do for 3 now. I want to try for. Let's do for 3. Let's do for 3. It's exactly the same idea. But I need you guys to wait. You guys cannot see the pattern unless you see two different, very different. What I'm saying now is that what we have done applies to 2, 3, 4, 5, 6, 7, 8, 9, 10. But you won't see the pattern unless we see two distinct ones, right? So let's say this is the polynomial. You guys should follow 2ab plus 3bc. These are our polynomial. What we want to do now is represent it in evaluation form. Okay? Multilinearly. Yes. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Right? But an hypercube of length 3. Now, we need all the evaluations here. Don't worry, that's just it. So if I vary this one, this is going to be 0, right? This is also 0. This is 0. This is 3. You said y? Who said y? Okay. Let's do it slowly. So this is A, B, C, right? So this is 2 into 0, 0, plus 3 into 0, 0. Does it make sense? So that's 0 plus 0, really equals to 0. Cool? Then this one is 2 into 0, A is 0, B is also 0, right? And C is 1. Cool? So that's still what? 0 plus 0. Then this one is, B is 1 now, right? So this is 0, this is 1, this is 1, this is 0. Everything is still 0. Now this one is B and C 1. So this is 0, 1, 1, 1. 0 plus 3, right? Then A is 1 here, which is just this. Then this is 0. Then plus 0, 0, right? This is what? Then this is A and C 1. This is 1. This is 0. This is 0. This is 1, right? Still 0. Then this is A and B. So that's 1, 1, 1, 0, right? Then this is 1, 1, 1, 1. Right? So now let me write it down in a right? So this is what 0, 0, 0, 3, 0, 0. Me and Francis have memorized this particular evaluation because we have used this so much. We actually memorized it.
0, 0, 0, 3, 0, 0, 2.
Yes. This specific one. That's why when I said like this is a famous polynomial, it's just because we have used this so much that we memorized this. So this is the evaluation form. Famous, just like we have used so much. Okay. Huh? Okay. 2ab plus 3bc. Does it make sense so far? Now we have 3 variables. What do you want to ask?
No, I'm not asking.
Okay.
I'm waiting.
You're waiting before you ask.
I'm not asking.
Okay. Okay, we have 3 variables. We can partially evaluate any one of them, right? Either A, B, or C. So you guys should choose. Which one should we partially evaluate? Oh yeah, if you want A, if you want B, if you want C,
What have a C?
they want C. C has it.
So you're going to do the graphical one too.
I will. It's very easy. It's possible, but only for this 3D. We can't do it for 4D easily. So let's do this now. We want to do C, right? You guys should follow. Follow. Yeah. Okay. C, right?
Yeah.
Let's say C is equal to 3. That's what I want to do. This is a cube, right? 3D. When we're done, we're going to have a square, right? Meaning that we have 1, 2, 3, 4, 5, 6, 7, 8. So we're going to have something that has just 4. It always halves. Remember when I was drawing this thing? Let's say I drew the line, then I copied the line. That's like doubling. Then I drew a square, right? Then I copied the square. That's like doubling. So when you're going from one dimension to the other, you're doubling the size. And when you're coming down, you're halving the size by 2. Make sense? Okay. So now, C is equal to 3. What we want to do now is find the places where C changes, but the rest of them stay the same. Okay? It's still exactly the same thing. So the way to easily do this is like, you just pick the first one. In this case, this. Look at what A and B. Look at what A and B are, and then find out where A and B is also that. That will tell you how to pair them up. Okay? So let's pair them up now. This one will pair with what? Right? So 0, 0, 0 is going to pair with 0, 0, 1. See, it's only C that is different there. Make sense? Then, next one is what? 0, 1, 0. I'm skipping this one right because I've already paired it. So 0, 1, 0 is pairing with what? 0, 1, 1. Another thing you could do is rather than looking for, just change it. Right? Just change the last bit or the bit that you care about to the opposite. For C, they are aligned. There's a pattern. For B, is somehow. For A, is a different way. You guys will need to understand this for implementation.
So you said it, you can either you make it 2 bits or you can flip.
Yeah, so you can flip the bits there. So let's say like this one now, right?
Instead of moving letters.
No, we're trying to pair them up, right? That's the goal now. So let's say like 100 now. What will it pair with? We just change the C value to 1 and find where that is. You get what I mean?
Yeah, A and B must be the same.
Yes, A and B must be the same. So you just see that changing. Does it make sense? So the next one is what? 100, right? 100, 101, which is here, right? And then 110, 111. So this is how we pair. So we already know that this is going to give us 4 new values, which is like half of the 8 values that we had initially. So what we need to do is just so easy. Figure out what the actual concrete values are, right? So what was 0, 0, 0? 0 and what?
0.
What was this one?
0, 2, 3.
3.
Is that 3?
Yes.
Yes.
This is 3. Make sense?
Yeah.
Ah.
No, you understood.
We're doing for 3 now. We're doing for 3 now. Okay. What is 100? What is 100?
0.
And 0.
0.
So why don't we have a vertical one?
What do you mean?
Why is there zero?
No, this is not. It's not related to graphical, horizontal. It's not related. I'm just like, these two create a straight line. I don't know whether a straight line is horizontal or vertical. I don't care about that in this case. Do you get what I mean? Do you get what I mean?
Yeah.
I'm never going to write it like this. 0 is paired with 0. Regardless of whether it is actually like that in the graph.
Yeah.
I'm just pairing and writing what the equivalent pairs are. You get, regardless of whether it's like this or like this, the formula is still the same, right? I will still interpolate and get a line, and then evaluate that line at the point. So when I'm talking in this sense, I don't care whether it's horizontal or vertical. I'm just like, these two pairs is fine. I don't even know where A is pointing right now, or where B is pointing, or where C is pointing. I don't care about that in this case. You get? And your algorithm too would not care about that. That's like level 2 understanding, when you want to do some more interesting stuff. Make sense? So what is 110? Good?
Yeah.
So now we're partially evaluating C at 3, and we have all the lines that we want to evaluate, right? So this answer will go to which index? Now this is where things get interesting. So this is what I was talking about last time. So C is different, right?
Yeah.
So this is going to what's common? What's common? 0, 0. Do you get?
Yeah.
So you just like remove C, and the answer will go to what is left. So this is going to 0, 0. This is going to 0, 1, 1, 0, 1, 1. Does that make sense? Which is like the same as the 4-element array. No, I'm telling you, like when we do the interpolate and evaluate, we'll have some answers, right? Like the same way it has 0 and 17. So you're trying to figure out where do you put it in the array, the result array. So that's like, I'm not telling you that this is where you put it. When you remove the C, that's going to be where you're going to put it. Do you get? This is equivalent to just like 0, 1, 2, 3. Right? In decimal representation. But don't worry about that yet. Let's just do the okay. I hope. It's a bit so sad. It's a bit so sad.
We have to come and have a
My battery. My battery is low.
You're charging your phone.
Okay. Yeah, it's still working.